Okay, Physics 12. We're going to keep working through our unit on electrostatic forces and electromagnetism. So we've previously been looking at first just electrostatics in general, and then we started looking at electrostatic forces. We looked at formulas in order to be able to find what is the electrostatic force in between two charged particles. We looked at an electric field and being able to calculate the intensity of that field and the force that a particular charge would experience while it was in that field. What we're going to be looking at today, continuing with that idea of electric fields and just electrostatic forces in general, is the idea of electric potential energy and electric potential difference. Okay, and then that will lead into our lessons on circuits later. Okay, so that's what we're going to try and work through in this lesson, and we'll go from there. Okay, so when we first start talking about electric potential energy, a big common example of that is actually lightning. Okay, and it's a huge, incredible example of that idea of electric potential energy. Now, while they still don't have all of the actual nuts and bolts figured out about exactly what's happening, not fully understood, the common concept right now is that when the water droplets that are in clouds move past one another, they'll actually pass a charge. And the electrons are transferred from rising water droplets to falling ones. And as a result, the negatively charged water molecules collect at the bottom of a cloud, right? Giving you a cloud that kind of, in very, very basic terms, looks something like this, right? So as the certain water particles will going up, right, they're passing other ones, passing on their electrons so that they sit down at the bottom of the cloud, okay? Now, when that happens, what that causes is obviously, looking at that shape, you have a very negatively charged bottom of that cloud that's closer to the Earth's surface, and that'll essentially cause like a charge by induction on the Earth's surface, right? So what's going to happen there is that, the Earth's surface will kind of be attracted to that, so the positive charges within the Earth's surface will kind of, come to the top of the surface and be more attracted to that cloud. And then again, that's an imbalance between the cloud and the Earth's surface, right? It kind of looks like a shadow. So if that imbalance gets big enough, right, the excess negative charge, the electrons in the cloud, might quickly be transferred from the cloud to the ground in the form of lightning, right? Electricity coming from the cloud and hitting the Earth, right? So the transfer of electrons from the cloud going towards that positively charged ground. Okay, so again, very simplified, as they kind of see it now, right? There's your electrons there, right? Your Earth has been kind of charged by induction, where it's kind of become overly positively charged, and eventually that just kind of causes that imbalance, and boom, there goes your lightning. Okay, all of that leads to the concept here is that when you do have a charge placed within an electric field, it will move. Okay, and the potential to move implies that there's the existence of stored energy, right? So if something can move and has kinetic energy, then that means at some point that energy had to have been stored. Okay, so we're going to be looking at that kind of idea of potential electric energy. All right, so you can kind of connect it very similarly to your potential gravitational energy, which is something we're a lot more familiar with, right? Where your potential energy essentially just means energy that's been stored. Okay, and it's equal to the work that would be done if the stored energy were transferred to kinetic energy, right? So if we went from, if we did a bit of work to convert the energy that's stored, right, the potential, and turned it into the kinetic energy, then, right, that would give us that value. So if you think back again to what we're a little bit more familiar with in terms of gravitational energy, right, gravitational potential energy, when an object falls, its potential energy, right, its gravitational potential energy, e.g., is converted to kinetic energy in one instant event, right? You're either stationary with a lot of potential energy or you're moving, right? And that instantaneous change of time, right, at that one instant, it switches. Okay, so again, if we're thinking about that rock on a cliff, if it's stationary and not moving, it has potential energy and no kinetic energy, and then the second it falls off the cliff, it now has kinetic energy. Right, and that potential energy is converted to kinetic energy instantly, okay? With electric potential energy, which we're going to denote by EQ, so just kind of try and keep some of these things straight, right? So in a previous lesson, it was FQ, right? That was our electrostatic force in between two particles, and then we had F with like the arrow over top, right? The vector quantity of the intensity of the electric field. Right now, EQ is our electric potential energy. Okay, so the electric potential energy is stored by doing work against an electrostatic force. Okay, so if we're working against the electrostatic force, that would mean that we'd be pulling unlike charges, like a positive and negative, pulling them apart, right? Because they would want to be attracted to each other, right? That would be the direction that'd be naturally going. So we would have to do work to pull them apart, okay? Or you'd be doing work if you were forcing like charges together, okay? Because again, if they were like charges, they'd want to repel naturally. So if we were pushing them together, that would require work, okay? So that electric potential energy is stored by doing that work against the electrostatic force. And again, we'll get into some of these things when we get into our lessons on circuits, right? But when we separate unlike charges, this is kind of like with what we do with the battery. And when we force together like charges, that's what's happening in a capacitor. All right. So your big difference here between your electric potential energy EQ and your your gravitational potential energy EG is that EQ, right, your electric potential energy actually involves a flow of energy that delivers over time. Okay, so it flows over time, whereas that gravitational potential energy that transfers instantaneously. Okay, so again, if you think of it in this terms of analogy, right, if you're trying to put out a fire slowly over time, right, putting out a fire with buckets, that would be kind of like with electric potential energy, or if you just had like a water bomber and one big poof, and it puts out the fire, right, that would be your gravitational potential energy. So there's kind of your big difference. So here's our formula, right? Looks familiar, again, similar to the one on gravitational potential energy, right, between two large masses, right, because of that same relationship between Coulomb's law, okay, and gravitational energy there as well. Okay, so again, this is the formula we're going to use. So again, slightly different than what we've seen before, right? Before you had FQ, which was the electrostatic force between two objects. It looked almost identical to this, except it was an R squared. Okay, that was the electrostatic force between the objects, was Coulomb's constant, multiplied by the two charges, divided by the distance between them squared. We're not looking for force now. Now we're looking for the energy, right? The electric potential energy between those two objects. So it's again Coulomb's constant multiplied by the two charges divided by the distance between them, right? And that gives you energy. Okay, so even just checking that out in terms of unit analysis, you'll see why, right? And I'll just kind of switch to the board just to kind of show you that there, right? So again, if we look at this new formula here with EQ, right, being K and then Q1 times Q2 divided by R, right? So this is energy, so we expect energy to be in joules, right? So again, remember, this is going to be Coulomb's constant, which is measured in Newton times meter squared over Coulomb squared, right? And then you're multiplying by a unit measured in coulombs, multiplied by another charge measured in coulombs, and you're dividing it by meters. If you start looking at your unit analysis here, you'll see your Coulomb squared will cancel here, and then your meters here will cancel here, leaving you with Newton times meters, which is joules. Okay, so that's where you're getting that energy from, right? Before, what we were looking at was the electrostatic force, and that was FQ over R squared, and then that would have been meters squared, which would have canceled the whole thing, and you just would have been left with newtons, right? Which makes sense for force, okay? What we're dealing with now is the electric potential energy with EQ, so that's just in meters, and it's Newton times meters, which is a joule, okay? So just kind of as a, yes, the formulas look very similar, but they do work out to give us the values that we're looking for, okay? All right, so with this one as well, keep in mind that we can get negative potential energy, all right? So EQ can be positive or it can be negative, okay? So what that means is you will actually just use the proper charges, right? When we were looking at forces, we just kind of took the absolute value of those charges and then gave them their direction afterwards based on where they were in the field and what their charge was, right? With this one, you can just use the actual charges on them, right? Positive or negative. Basically, all it's saying here is that if it's negative, it just means that the object's being moved in a way that decreases its potential energy, okay? And the force of the source field assumes some potential energy. So it becomes negative from its original position. Overall, EQ will be positive when charges are similar, as more potentially is stored when they're brought closer together. Okay, EQ will be negative when the charges are opposite and are attracted to each other, right? You don't store as much potential energy, right, if they're being brought together anyway, right? So similar to how EG was negative when thinking about a mass being attracted to a larger mass through gravity, right? So you remember that back when we did stuff with gravitational fields, right? And we kind of had that negative in front saying, okay, well, it's always going to be attracted to the larger mass, so the whole thing was always negative. This kind of the same thing here, right? The potential energy will be zero, right, when the charges of either type are an infinite distance apart, okay? So there is no potential energy if you are infinity distance away, okay? So there we go. All right, so let's just start with this first one, right? So what is the electric potential energy stored between charges of positive 8 microcoulombs and positive 5 microcoulombs that are separated by 20 centimeters? All right, so in this case, we've been given two charges. We've been asked what's the electric potential energy stored between them, and we've been given the distance that they're separated. Okay, so we can just go ahead and use that formula that I just defined in solving this problem. Okay, so there's that formula, right? So the potential energy, electric potential energy, right, Coulomb's constant, multiplied by the two charges, divided by the distance between them in meters, right? So we have our values where obviously Coulomb's constant is our 9.00 times 10 to the 9 Newton meters squared over Coulomb squared, multiplied by our two charges. So one, which was positive 8 microcoulombs, so positive 8.0 times 10 to the minus 6 coulombs. And then our second one was a positive 5, so positive 5 times 10 to the minus 6 coulombs there. And the distance between them was 20 centimeters, so we would put that into meters, and that's 0.2 meters, okay? And then just carefully plugging that into your calculator, and again, you'll notice the units here, those will cancel here, one will cancel here, and you're left with a value of 1.8 Newton meters, or EQ being 1.8 joules, right? So the potential energy stored, electric potential energy stored between them is 1.8 joules, right? And again, it makes sense for this value to be positive because both of those charges were positive, right? They were both like charges, right? It's negative, so like work had to be done, right? Trying to keep those together because naturally they wanted to pull apart because they're the like charges. Okay, let's go back here. No, play. Here we go. Okay, so again, there we go. With this one, just in the interest of time, I am just going to leave these for you to try. So feel free to just kind of pause the video. Nothing crazy here other than just another sample problem, right? Finding electrical potential energy stored between two other charges here, right? Again, you'll notice one is positive, one is negative, and notice how now your answer is negative here, right? Because they are unlike charges, okay? And here you're just rearranging the formula, right? So how far apart must two charges be, one being positive, one being negative, in order to have that electric potential energy with a magnitude of 2 joules, right? And again, you notice that concept of, okay, well, one's positive, one's negative, and in this case, they're going to have to be very, very much separated in order for that answer to have to be a positive work done. Okay, so just take a few minutes. If you really can't get them and you're not getting these answers, shoot me an email and I will send you off the full solutions to these. All right, but other than that, we're going to kind of keep going here. All right, so that was just electric potential energy, right? But we also need to discuss the idea of electric potential difference. Okay, so I mean, it's, you know, kind of as the name implies, it's the difference in electric potential energy of a unit charge between 2 points in an electric field, okay? So in this case, we don't necessarily need to think about two charges per se, right? So in that other one that we were just electric potential energy, you were looking at two specific charges where you needed the value of both of them to be able to calculate what that potential electric potential energy was. With the electric potential difference, you're really just dealing with a single source charge, right? And then it's just a random unit charge. Okay, so we don't need to know the value of the charge being brought into the field, all right, the electric field. We just need to know, well, what's the value of the source charge, okay? And then it's the difference between the potential energy between 2 points. So if that unit charge was at point A and then it was at point B, right, what would be the potential energy difference from going from one point to the other, okay? So just to kind of explain that a little bit more, right? So like that difference between electric potential energy versus the electric potential difference, okay? So there is a definition difference between them, obviously, because they're two different things. So electric potential is defined as the work necessary to move a unit positive test charge from rest at infinity to any specific point in the field of Q1, right? So something is the source charge, okay? So we talk about just general electric potential, right? It's defined as the work necessary to move a unit positive test charge, right? So again, we're dealing with that positive charge from rest at infinity, right? An infinite distance away from that source charge and being brought to a certain point in the field of Q1, right? But when we think about, charges within a field, we're not typically thinking about, well, how much work is it going to take to bring them from infinity? It's more about, well, how much work is it going to take them from point A in the field to point B in the field? Okay, and that's really what we're dealing with here. So what you would really do is figure out, okay, well, what's the difference, right? So what work is required? What's the work required to bring it from infinity to point A? What's the work required to bring it from infinity to point B? And then the difference between those is how much work is it going to be to bring it from point A to point B, right, or vice versa. Okay, so your electric potential difference is defined as the work necessary to move that unit test charge from point A to point B. Okay, and that's where it's coming from. Okay, so how we find that then, like I said, because it's a unit test charge that we're dealing with, we don't need to know the charge on that value, right? What we do need to know, though, is the source charge. Okay, so our electric potential difference, also measured in volts, right? Or I think it's newtons per coulomb is the other way to deal with it, right? Is a relationship here where, again, coulomb's constant, multiplied by that electric charge, the source charge, divided by the distance, okay? Distance of, the other, the point charge being brought into the field, okay? So that's how we're going to be finding the electric potential difference, right? And then you would find that for, to point A, and then you might find it to point B, and then you subtract the two to get the difference, right? So let's go into a sample problem for that one. All right, so what we have is a small sphere here with a charge of negative 3.0 microcoulombs. It creates its own electric field. Calculate the electric potential difference at point A, which is located 2 centimeters from the source charge, and at point B, located 5 centimeters from the same source charge. Okay, so we don't need to deal with angles here or anything like that, right? It's just purely a scalar quantity. So what we're dealing with here is being able to figure out, okay, what is the electric potential difference here and here, right? And then what's the potential difference between A and B? Okay, so let's do that again on the board. Okay. So, with that one, so again, what you've got is here is our small sphere. It has that charge of negative 3 microcoulombs, right? We have point A over here. That distance is 2 centimeters away, and then we have point B down here, and that distance is 5 centimeters away. Okay, so we're going to find what is, find the electric potential difference for point A, for point B, and then we're going to do the difference between them. Okay, so if we start and we look at that potential difference for A, right? It's K times Q divided by R. So there's our Coulomb's constant multiplied by our charge, which is our -3, right? And we are using signs here. And we're dividing it by our distance, so we have to convert 5 centimeters into, oh, sorry, this was 2 centimeters, so 0.02 meters. And that gives us a value of -1.35 times 10 to the 6 volts, okay? Or if we again looked at that unit analysis, that cancels with that cancels with that. So it's Newton meters. Okay, so I had that wrong before, but it was Newton meters per Coulomb, or that would again be just joules per Coulomb. Okay, so there's our electric potential difference for A. Technically, if we're dealing sig figs, we only get 2 here, so really it's like -1.4 times 10 to the 6 volts. Okay, we're then going to do the same thing for B. So we just change this value, right? That constant is the same. Source charge is the same. It's just the distance that's changing. So we change that to a 5, okay? And then that gives us a value here where that electric potential difference is -5.4 times 10 to the 5 volts. Okay, so those were kind of the answers to part A, which what was the electric potential difference for the two. And then it's now asking, if we just go back to the question, right, what's the potential difference between A and B? Okay, so we just calculated the electric potential difference at point A, and we calculated the electric potential difference at point B, and now we're trying to find the potential difference between A and B. All right, so if it's difference, it's just subtracting the two. Okay, so what we're going to need to do here, I need to switch this, there we go. So for part B, right, we are looking for what is VB minus VA, right? That's what we're looking at there. So we had VB given to us, was that -5 point, or not given to us, we calculated it, -5.4 times 10 to the 5 volts, and we're subtracting what we calculated for VA, which was -1.4 times 10 to the 6 volts there. Okay, so I guess this is really what we're doing. Not AB, not VA. Okay, so when we do this calculation here, right, it's just, so it's this minus this, and we get a value of a positive 8.6 times 10 to the 5 volts. Okay, so there's the electric potential difference to go from one to the other. All right, and again, you're seeing that that is positive, right? Because again, if we're thinking of all of these as positive point charges, right, because that was in the definition for our electric potential difference, it's about a positive point charge being brought into a field. So this positive point charge is being brought into a field where it's negative source charge. So this is kind of how our field lines are looking, right? So A, of course, would be wanting to be drawn into that field, right? That's kind of the natural feeling that it wants to do. So if we wanted to try and move the point charge from A and then move it to B, that's going to take work, right? We are going to have to put work into that in order to get it to go from here to here. So that's why this potential difference is positive, right? Because this is implying here, right, that VB is bigger than VA, right? Just because, again, it's going to take work to move it from point A to point B, because obviously it would rather be pulled in this way, and you're trying to pull it away from it, which is in opposite of what it would want to do naturally, right? So that's why that value is positive, Okay, obviously you'd get a different answer if you switched it the other way around, and a positive point charge would be happy to go from B to A, and then that would give you a negative answer. Okay, so that's kind of what's happening there with those fields. And back to this, okay? Here we go. All right, so again, there's your same values. Apparently I used different rounding values for some strange reason and got a slightly different answer, but we'll go with it. Because I think I kept that, I put that as 1.4 instead of that, so that kind of messed it up. But same concept applies. All right, so let's move on to sample problem number 3. All right, so in this one, you have a charge of positive 6 microcoulombs at point A is separated 10 centimeters from a charge of minus 2 microcoulombs at point B. At what locations on the line that passes through the two charges will the total electric potential be 0? Right? So essentially, if we're talking about total electric potential, we're talking about the sum, right? Just the algebraic sum of the electric potential of some point, right, on this line with A and with B, and then adding them together, getting an answer of 0. Okay? Now, what I want to show you before we get into that is just kind of a visual representation, right? So this is another one of those applets that allows us to kind of see things, and I'll post the website for this if you want to play around with it a bit on your own, right? But just kind of showing the grid, here's essentially what's happening, right? We had this charge, and I'll kind of put it here. It's not going to be exact because they've got these as nanocoulombs, but I'm just going to kind of do them at the same scale, right? So 1, 2, 3, 4, 5, 6, okay? So again, what you're seeing there, right, is that field lines, right, going away from the positive, okay? And then what we have along this straight line, so I've input the grid here, we can put just 2 of these negatives this way, right? So again, you're seeing these field lines, right? So going from positive out into the negative, these lines would never actually cross each other, right? And this is kind of what's happening, right? So they kind of circle up and around, right? These ones kind of continue to go up and around and through, right? Up, over, down and through, and these kind of radiate out, okay? Now I'm going to use this little voltmeter because we want to find out when, so this is actually measuring equipotential, right? So when are they kind of equal, which is what we're looking for. When is the sum of them 0? And if we kind of go across this line, right, that connects them, see when is that value somewhat 0, right? Just to give us an idea, okay, of what our potential is. So going across here, we see that that equipotential is very, very positive on this side. And as we move closer to the negative, it becomes less positive. And until we get to a value that is 0 and then switches over to negative, right? And we can see clearly here that it's more than halfway. So we can anticipate from this that a point will be somewhere, right, where the sum of the electric potential to 0 is going to be somewhere along this line, but likely closer to the negative charge, right? Because this one was a larger charge, right? It was plus 6 versus minus 2, okay? So there's one spot. We also haven't been restricted at this point into just between them, right? So we could also look continuing out along that line, right? So again, you notice as we get closer here, it becomes very negative, right? And then we pull away, it's still negative, but you'll notice it's becoming less negative, right? But again, you see these positive charges, they are still having an effect as they circle around and come this way. So it does end up becoming, right, so first it's becoming, yeah, and then less negative, less negative, less negative, and then switches to pretty much 0 and then back over positive. So we can also anticipate a point beyond that negative charge as well, having that equipotential or that sum of those two charges being 0 as well, right? Because you still have a positive influence coming up and around here, okay? And then it would be, again, you've got the negative pulling this way, but then the positive coming all the way around here, okay? Now, if we tried along this side, you'll notice that yes, that value is getting less and less, but not to a point where we're really going to be able to get to 0, right? And you'll even kind of notice that that's not going to make any sense because that negative is, because it's smaller and because it's over to the right, it's not going to have that same effect as it is all the way over here, right? This is just going to end up out at infinity, and that negative point charge isn't having anything to do with it anymore, right? Or sorry, negative source charge, right? Part of that field. So really, we're looking at two possible answers here. One that's somewhere in here, right? Closer to the negative charge, and then one that's out here as well. The question is now, how do we just figure that out algebraically? Right, so there's kind of the visual of what's happening. Let's now take a look at the algebra for it. Okay, so where did my marker go? Here it is. So as mentioned, what we want here is we want our sum to be 0. All right, and that's going to happen in this case, right? That could be one of our cases, or you can think of it this way. Right, so either where VA is equal to negative VB, or VA is exactly equal to VB. All right, so the other way to look at it is essentially this way, where it's like the voltage at that point due to A, right? We want that magnitude. In both cases, the magnitudes are the same, right? It's going to be equal to the voltage of that point due to B, right? Now, because we're thinking of the magnitudes being the same, mathematically, you're solving this as like it's an absolute value equation, right? Where whenever you have absolute values, you have two cases. So in case 1, you have this, right, where you just remove the absolute value signs and you just say, okay, this value is the same as this value. Or in case 2, you can remove the absolute value signs and say, okay, well, this one is now equal to the negative of that one. So we have to look at it in two possible ways. So let's just look at it in the first way, where when we remove them, we get this one, right? So this would again be setting up, right? So this is kind of like the first scenario. I just felt. All right, so this is scenario number 1, right, where we're just setting up VA equal to VB, right, using our equation that we've come up with, right, so that's K QA over R, which now, thinking about it, we don't know the distance between them, right, that's what we're actually trying to solve for, is this idea, right, so if we, remember you've got this one, that's the positive, and then this one is the negative, and we've said there's going to be some sort of point here, and then there's going to be another point somewhere out here, right? Now, we were given in the question that the distance between these is 10 centimeters, right? So if we call this the distance we're trying to find, right, from A, essentially, right, and that's B, we can call this D, so that would go in there. So this would be our 9.00 times 10 to the 9, multiplied by our charge, which was, in that case, Q of A was plus 6 microcoulombs. So 6 times 10 to the minus 6, divided by, and we're going to call that D, right, because the distance, the point is away from A. And that's going to equal, again, our Coulomb's constant, multiplied by our charge, which was, in this case, it was minus 2 microcoulombs, so negative 2.0 times 10 to the negative 6. And this value here would be 0.1, right? So if this is 10 centimeters and this is D, this is 10 minus D, but we had to put it in meters, so it's going to end up being 0.1 minus D for that one, okay? At that point, I'm going to have to erase this, okay? At that point, we need to cross multiply to solve, okay? So if I cross multiply here, well, I can do this math and do this math, and what you get doing this is a value of, I'm looking at my wrong example, so you get 54,000. Units here would be Newton meters squared over coulombs, because one of these coulombs cancels with this one. divided by D is equal to, and then you do this, and you get negative 18,000 Newton meters squared over coulombs divided by 0.1 minus D. You cross multiply here, so you get 0.1 minus D times that 54,000. I'm going to drop my units now for a second, and then cross multiply here and get negative 18,000 D. Okay? And then from there, distributed property on this. So this now becomes 5,400 minus 54,000 D is equal to negative 18,000 D. Bring your D's together, so you get 5,400 is equal to this negative 18,000 plus, right, 54,000, which gives you a positive 36,000. Divide both sides by 36,000. And what you get is a value of 0.15, and that's meters, is distance. Okay? Now that was distance from point A, right? So remember going back here, this was A, this was B, right? We said the distance between them was 0.1 meters. So this value of D here, right, indicates that it's that point out here, right, which is actually 0.15 meters away from A, right? And we saw in our little applet that this was a point that would work, right? Because it's still being affected by that, because this is a greater positive charge, right? It has a greater reaching field than this negative one, right? So it does still have an effect there for that positive, less positive, and more negative to kind of cancel out there, okay? And then what we need to do is look at our other options. So now we look at scenario 2. Right, so again, when solving like absolute values, in scenario 2 here, you've got your VA is equal to your negative VB. So again, that's your K QA over R is now equal to negative K QB over R. So same idea here, right? This is our 9.00 times 10 to the 9. This was our positive 6.0 times 10 to the negative 6. This was our D, right, the distance that point P was away from A, right? This is now negative 9.0 times 10 to the 9, multiplied by that charge of negative 2.0 times 10 to the minus 6, all over that 0.1 minus D, right? Same concept here, get these values multiplied. You get a value there of, again, 54,000 divided by D is equal to now negative times positive is going to give you a positive 18,000 over 0.1 minus D. Cross multiply again here, right? So when you do that, you end up getting 5,400 minus 54,000 D is equal to 18,000 D, right? Once again, so add your 54,000 to both sides. What you get then, this is coming up here now, right, is you get 5,400 is equal to 72,000 D. Divide both sides by 72,000. Oh, that doesn't cancel. But you end up getting a value there of 0.075 meters is equal to D, right, which is the same as 7.5 centimeters. Okay, so we've got our two answers now. Again, both of them were from point A because of how we defined the value D, right, was using that distance away from charge A. Right, so again, what that looks like is the following, right, where you have this charge A here, that was a positive 6. You had this charge B here at minus 2. And the distance here was 10 centimeters. So we had a point P that was about 7.5, right? So 3/4, right? The sum of their electric potential differences was 0 there. and then there was another one 5 centimeters away here, where again the sum, and again that matches exactly with what we saw in our field simulation. Okay, and back to this. Okay, and there you go. So, last final example here to look at, right? So in this one, 2 charges are placed at the corners of a square. One charge, being positive 3.7 microcoulombs, is fixed to one corner, and another charge with value of negative 4.5 microcoulombs is fixed to the opposite corner. What charge would need to be placed at the intersection of the diagonals of the square in order to make the potential difference 0 at each of the 2 unoccupied corners? All right, so again, let's try and draw this out and see what we can come up with. All right, so we've got a square. That's easy enough to draw. Okay, we have 2 charges on opposite corners. So if we call this one A, that was given to us as a charge of positive 3.7 microcoulombs. On the opposite corner, we'll call that B, right? That was given to us as a charge as negative 4.5 microcoulombs. We are wanting the voltage here at point C, or actually I'm going to call this point C because we're trying to figure out what charge that is. Okay, I'll call this D, and I'll call this point here E, right? We want the voltage, the sum of all of the potential electrical energies at D to be 0 volts, right? And the same thing would be here. Nice thing about this being a square is that we don't need to do this twice, right, to think about it, because this is going to have the same potential energy here as it does here, right, and so does this one on these 2 as well. So what's happening here is going to be happening here, and this is being placed exactly on the diagonal. Okay, so we want the charges here, right, the electric potential difference here, to the sum of all of those electric potential energies to be 0, right? So we basically are saying we want the voltage from A and the voltage from B and the voltage from C, right? We want all of those electric potential differences, when added up on this point here, to equal 0. That's the goal, okay? We can figure out this and this, and we're trying to look for that charge, okay? So again, these all have formulas, right? So this would be K QA over R, RA, this is K QB over RB, and this is K QC over RC. K is not a problem. The charges are not a problem. What you'll notice is that we don't have any information right now about the distances, right? So what we do know, though, is that this is a square. So if we call this X, we can also call this X. Okay, so in kind of continuing with this, but just down here, right, I can set up, right, so it's 9.00 times 10 to the 9, multiplied by my positive 3.7 times 10 to the minus 6, divided by X, plus this one here, same thing, 9.00 times 10 to the 9, multiplied by negative 4.5 times 10 to the minus 6, divided by X. And then this one is again going to be that K, so 9.00 times 10 to the 9, multiplied by QC, which I don't know, and the distance here I need to kind of get an algebraic expression for, right? It's half of the diagonal, okay? So if this is X and this is X, right, and this is a square, then this entire diagonal, or this entire diagonal, same thing, right, is going to be found using Pythagorean theorem. So x squared plus x squared is going to equal that diagonal, right, squared. So the length of the diagonal is just the square root of 2x squared, right? Add those together, you get 2x squared, you square root it, you get d, okay? But I only want half of that, so I cut that in half, right? And what this value is right here is just root 2 over 2 times x, right? Because I can break that up so that it looks actually like root 2 times x, right? Because the square root of x squared is x, and then I'm cutting that in half, okay? So that's my value of my radius here, is root 2 over 2 times x, and all of that is equal to 0, okay? I can get this value, I can get this value, they're both over x, which means that I can just combine them into a single term, right? So this ends up being a positive 33,300. This is a value of negative 40,500, and then when I add them together, I get negative 72,000 all over x, right? Because they have the common denominator, so I can add them. And then what I'm going to do is I'm going to bring this over to the other side, right? Because it's equal to 0. And say that's now equal to negative 9.00 times 10 to the 9 multiplied by that charge on C divided by root 2 over 2 times x, right? Now, again, you could do some cross multiplication here, right? And then what you'd end up having is this negative 7,200 multiplied by root 2 over 2 x is equal to this value here of the negative 9.00 times 10 to the 9 times QC times x. And then it doesn't matter what the distances here were, because the fact that they were a square works out perfectly, because this x will cancel with this one here, and our only variable we're left solving for is the charge on C, which is the thing we were looking for in the first place, right? So now, this is just a matter of saying, okay, well, what's negative 7,200 multiplied by root 2 over 2, and then dividing it by negative 9.00 times 10 to the 9, okay? And then when we do that, we get a value of 5.657. We only get 2 sig figs, so let's just call it 5.7 times 10 to the minus 7 coulombs on C for that to work. All right, so even if you're not given the distance, if it was a square like that, you can still solve it just based on proportional reasoning, okay? So that is, that's all the work that I've got and examples that I've got there for the electric potential energy and the electric potential difference. Oh shoot, I forgot to change the page number again for you folks, so let me quickly look that up. That was from the old version, the other version of the textbook. This is actually in your textbooks on page 678. All right, so really you're on page 678. It's the same question numbers though, 42, 43, up to 58 there. Okay, same types of concepts there in solving. I'll also post the link to this little applet, right? It's another one of those little things. I don't think this one requires Flash. I think it's just HTML5. So you might be able to play around with that a little bit if you'd like to, in terms of just kind of seeing charges and fields and kind of the lines that are drawn in there. And you can work on those questions. And then we'll get into circuits next. And we'll save electromagnetism for like a separate thing next week. Okay, so there's the plan.